Welcome back, everyone. Today, we're diving into something that's been a bit of a head-scratcher for centuries. Prince Rupert's drops.
Oh, yeah, those are fascinating.
Ever seen one of these
I
things?
have, yeah.
They're like little glass tadpoles, right? Unbreakable heads. But you snap the tail and the whole thing just explodes.
It's pretty wild.
The poet, Samuel Butler, once called them glass bubbles, and he wasn't too far off.
Yeah.
They're this crazy mix of strength and fragility. So in this deep dive, we're going to try to figure out how they're made, how they break, and what those fragment patterns can tell us.
Sounds good.
And trust me, there are going to be some surprises along the way.
What always gets me is that making them seem so simple, right?
Yeah.
You just take some molten glass and plop it into water.
Yeah.
But the physics going on under the surface,
Yeah.
seriously complex.
Let's unpack that then. What makes these drops so explosively fragile?
It all boils down to how they're formed. When that molten glass hits the cold water, the outer layer cools and hardens super fast. Quenching, we call it. But here's the thing. While the outside is going solid, the inside is still molten.
So there's like a time delay.
Yeah, exactly. So as the inside cools down, it contracts, pulls on that hardened outer shell, and you end up with a huge amount of internal tension.
Like a spring that's wound way too tight.
Exactly. And snapping the tail is like messing with that balance. All that stored up energy, it's got to go somewhere.
Yeah, boo, it explodes.
Exactly. Shatters violently.
Okay, that explains the whole explosive thing. But in the research you sent over, there was also mention of quench granulation. What's that all about?
Oh, good catch. That's what happens when you don't get a Prince Rupert's drop at all. The molten glass, it just disintegrates on contact with the water.
Oh, wow.
Shows you that the cooling process has to be just right for that super strength to emerge.
So it's a delicate balance, huh? Cooling and solidifying. A narrow window for that strength. The research you showed gets even more interesting, though.
Yeah.
They tested how these drops break in different mediums. Not just air, but water and even syrup.
Oh, right.
What did they find?
It's pretty surprising, actually. The medium. Big impact on the fragmentation. Breaking them in air, you get tiny pieces, almost dust, but in syrup. Much larger fragments.
I wouldn't have expected that. Does the syrup cushion the explosion somehow?
Not really. It's about how the fractures spread. They need space to grow.
Yeah.
Syrup, being much thicker than air, it resists that expansion. Like imagine running through honey versus running through air.
Yeah,
You're
okay.
going to get slowed down on the honey, right? Same principle. The syrup slows those fractures down so you end up with bigger pieces.
Makes sense. To see all that in action, they must have needed some seriously fancy imaging techniques.
Yeah, they use something called microcomputed tomography, or CT for short.
Catchy.
Think of it like a super detailed three-dimensional X-ray. It let them capture images of those fractures as they were happening at a microscopic level. And that's how they discovered something else really cool. The patterns formed when a Prince Rupert's drop breaks.
Are we talking about fractals here? Those endlessly repeating patterns you see in nature, like in snowflakes?
We got it. Those patterns show up in broken Prince Rupert's drops, too. Scientists use something called fractal dimension, DM, to measure how efficiently something breaks apart. Higher the D. More small fragments you get, relative to large ones. A measure of how thoroughly something shatters, basically.
So a drop that turns to dust would have a higher D than one that breaks into a few big chunks.
Exactly. And the drops broken in air, the ones that shattered the most completely, had the highest DM. Which makes sense, thinking about that resistance from the medium we were just talking about. Air puts up the least resistance.
This is already blowing my mind. All this complex math and physics hidden inside these little glass drops.
Right.
But what does this fractal stuff tell us about the world? Why should we care how shattered glass is organized?
It's about more than just these drops. Understanding how things break under stress, how that's affected by outside forces, has applications everywhere. Designing safer buildings. Figuring out how rocks fracture during earthquakes.
Okay, now I see it. Something that seems like a niche scientific curiosity can actually have some pretty big implications.
It can.
And we're just getting started, right?
Oh, yeah. We haven't even talked about the shapes of the fragments themselves.
Yeah.
And those shapes, they can get really diverse, depending on where they came from within the drop.
The material you sent mentioned something about plate-like fragments versus blocky shapes.
Right.
What's the difference there? And why does it matter?
Well, those ETT images, they gave researchers an incredibly detailed look at individual fragments. What they found is that the outer layer of the drop, the part under the most compression, it tends to shatter into these super thin, almost paper-thin pieces.
Like safety glass shattering.
Exactly. Thin shards instead of big chunks. And those plate-like fragments, They're a direct result of how those compressive forces act on the glass. But the inside of the drop, that's a different story. The fragments there are much chunkier, more irregular, almost like, well, I guess you could compare them to irregularly shaped dice.
So you've got these two distinct types of fragments, and they're telling us about the forces inside the drop.
They are.
But there's another layer to this, right? You mentioned something about voids inside the drops affecting the fragment shapes, too.
Absolutely. Those voids, essentially little bubbles trapped in the glass, act as weak points. When the drop breaks, the fractures tend to go around those voids, leading to some really unique fragment shapes.
It's like each fragment is a clue, revealing a bit more about the drop's life, from formation to its explosive end.
I like that.
But hold on, there's one more twist we haven't covered. What happens when you add bubbles to the molten glass before it's even quenched?
Oh, that's a good one.
The results were, well, unexpected.
They were. Adding bubbles completely changed the outcome. Instead of those super strong drops, the glass just fell apart, couldn't even hold its shape.
So adding bubbles actually prevented the drops from forming. That seems counterintuitive.
It does. What the researchers found is that those pre-existing bubbles, they interfere with the quenching process. They create uneven stress points in the cooling glass.
So instead of that smooth, evenly compressed layer, you've got these weak points, and the whole structure becomes unstable.
Exactly. It's like trying to build a house of cards on a wobbly table. The foundation's not there. And this finding, it actually has some interesting implications for understanding volcanic eruptions.
Oh, now you've got my attention. How do bubbles in glass relate to volcanoes?
Think about it. Lots of volcanic eruptions involve magma, molten rock, that's full of gas bubbles. And when that bubbly magma hits water, it can trigger some seriously violent explosions.
The kind you see in, like, Iceland or Indonesia.
Exactly. So if we can figure out how bubbles change the way glass breaks apart, it gives us clues about how magma might behave during those eruptions.
Now I see the connection.
It's a great example of how a seemingly simple observation can lead to insights into much bigger, more complex natural phenomena.
I love that about these deep dives. They uncover all these unexpected connections between different areas of science.
Mine too.
And speaking of connections, we're about to explore an even deeper one. Stick with us, because next, we're going to look at how the size and shape of those tiny glass fragments can actually tell us a story about the drop's history. It's like microscopic forensic science.
Like that, microscopic forensic science. We're going to delve into that microscopic world and see what secrets we can uncover. Stay tuned. Welcome back to our deep dive on Prince Rupert's drops.
Last time we were talking about those tiny glass fragments being like clues at a microscopic crime scene.
Right.
So let's put on our detective hats and see what they tell us about a drop's history.
It really is amazing how much information is hidden in those fragments.
Like what?
Well, for starters, the size and shape can reveal a lot about the cooling process.
Okay, remind me again. How does cooling play into all of this?
Remember those voids we talked about? Yeah. Those little bubbles that form inside as the drop cools.
Yeah.
The size and distribution of those voids actually leaves a fingerprint on the fragmentation pattern.
So a drop with a bunch of big voids would break differently than a drop with just a few small ones.
Yeah, exactly.
Huh.
Those voids act like weak points in the structure.
Okay.
They influence how the stresses build up and how the drop breaks apart in the end.
It's like looking at a cracked windshield, right?
Yeah.
The pattern of the cracks can tell you where the impact happened.
That's a great analogy. By analyzing the fragments, we can kind of reconstruct a map of the stresses within the drop.
So we can see where the tension was highest and where
Okay.
the compression was strongest.
Exactly. We can even see how the voids change the stress patterns.
It's like having a time machine, huh?
It is.
Seeing how the cooling process unfolded inside.
Yeah.
Amazing.
But there's more.
Yeah.
The material you sent also mentioned how the shape of the fragments varies depending on where they came from within the drop. Right. The researchers, using those CT scans, were able to analyze the shapes of individual fragments in incredible detail. They found some very clear patterns.
Remind me about those patterns again.
Okay, so fragments from the outer layer, the part under the most compression,
Yeah.
they were typically very thin and flat, almost like little plates.
Like safety glass shattering into those flat shards.
Exactly. Those plate-like fragments are a direct result of the compressive forces acting on the glass.
Gotcha.
But the fragments from the inner part of the drop, the area under tension,
Yeah.
Those are more blocky and irregular.
Like those jumbled dice we were talking about earlier.
Right, so basically the shape of each fragment is like a little signature.
A signature.
Yeah, telling us about the forces that were acting on that specific part of the drop.
Each piece telling part of the story.
Exactly.
But let's not forget about that surprising finding with the bubbles.
Oh yeah, the bubble mystery.
What happened again when they added bubbles to the molten glass?
Adding those bubbles totally messed up the formation of the Prince Rupert straps.
Yeah.
They couldn't even hold their shape.
It's like the bubbles worked against the forces that usually make the drops so strong.
Right. It's counterintuitive.
It is.
So how did the researchers explain that? Well, they concluded that those pre-existing bubbles messed with the balance of stresses during cooling. So instead of a smooth, evenly compressed outer layer, you end up with these weak points where the bubbles were.
Oh, like little ticking time bombs, just waiting to go off.
Pretty much. It shows just how sensitive the whole process is.
Yeah.
Even tiny disruptions can totally change the outcome.
And you were saying this has implications for understanding volcanoes.
It does. Think about it.
Okay.
Lots of volcanic eruptions involve magma, molten rock that has a bunch of gas bubbles in it.
Yeah. Okay.
And when that bubbly magma comes into contact with water, it can trigger an incredibly powerful explosion.
The kind that can change landscapes.
Exactly. So studying how those bubbles affect the way glass breaks apart gives us clues about how magma might behave during those massive eruptions.
I'm starting to see the connection.
It's a great example of how studying something simple can give us insights into the most powerful forces on the planet.
This is so cool. It's amazing how something as small as a Prince Rupert's drop can open up so many avenues for research.
I know, right?
But we've been talking about the past.
Yeah.
What about the future? Could we use this knowledge to engineer materials that break apart in specific ways?
Now you're thinking like a scientist. That's a question researchers are working on right now.
So instead of just watching these drops break naturally,
Yeah.
we could actually control the process, create drops that shatter in very specific, predictable ways.
That's the idea.
Wow.
We could, for example, control the size and distribution of those voids
Okay.
and create drops that release their energy in a very controlled manner.
I mean, what kind of applications are we talking about here?
The possibilities are pretty huge. Think about demolition. Instead of explosives, you could have these precisely engineered drops that shatter with a specific force.
So much cleaner and more controlled.
Right. And then there's energy storage.
Energy storage.
We could design drops that store mechanical energy and release it when they shatter.
Like little glass batteries.
Pretty much.
Okay, my brain is officially melting.
And then there are the medical applications.
Tiny exploding drops in medicine. That sounds like sci-fi.
It's cutting edge, but the potential is there.
Like what?
Imagine using these drops for targeted drug delivery.
How would that even work?
You could design them to release medication only when they get to a specific spot in the body.
So you're minimizing side effects.
Exactly.
Wow.
It's all about understanding and controlling those principles of fragmentation.
This has been an incredible journey.
It has.
We've gone from historical curiosities to the cutting edge of science.
We have.
And it seemed like we've only just scratched the surface of what there is to learn.
Always more to discover, even in something as simple as a drop of glass.
We've given our listeners a lot to think about.
We have.
And I'm sure they're wondering what's coming next.
Oh, yeah.
So stay tuned, because in the last part of this deep dive, we're going to explore some even crazier ideas about the future of Prince Rupert's drops. Welcome back to the final part of our deep dive into Prince Rupert's drops.
It's been a wild ride, hasn't it?
It has, from those weird properties to the connections with volcanoes.
Right.
We've covered a lot.
Yeah, it's amazing what you can learn from something as simple as a drop of glass.
And we're not even done yet.
No.
In the last two parts, we explored how these drops are made,
Right.
how they break, what we can learn from those fracture patterns.
Uh-huh.
But now I really want to hear more about that engineering aspect.
Oh, yeah, the engineering part.
The idea that we could engineer these drops for specific purposes.
That's where the research is heading, yeah.
How do we even engineer something that seems so, I don't know,
Yeah.
chaotic, with all the heating and cooling?
It's all about control.
Control.
Remember all those factors we talked about?
Yeah.
Cooling rate,
Mhm.
bubbles, the surrounding medium.
Uh-huh.
Well, the key to engineering these drops is gaining precise control over those factors.
Okay, so instead of letting nature do its thing, we step in and fine-tune the process.
Exactly.
Create drops with specific properties.
Like, imagine tailoring the size and distribution of those internal voids, the bubbles.
Okay.
We could potentially make drops that shatter in a very controlled way.
So they release their energy in a specific way.
Exactly.
This is getting pretty sci-fi.
It is, yeah.
But what kind of real-world applications are we talking about?
Well, think about demolition.
Okay.
Instead of explosives, you could use these engineered drops that shatter with a specific force.
Oh, wow.
You target just the structure you want to take down,
It's much more controlled.
right? And then there's energy storage.
Energy storage?
Yeah, you could design drops that store mechanical energy
Hmm.
and release it when they shatter.
Like little glass batteries?
Pretty much.
My brain is hurting.
I know, right? And then there are the medical applications.
This is the part I'm most excited about.
It's definitely cutting edge, but the potential is there.
I mean, tiny exploding glass drops in medicine. How?
Imagine targeted drug delivery.
Okay.
You could design these drops to release medication only when they reach a specific place in the body.
Wow. So you're minimizing side effects.
Exactly.
It's incredible.
It's about understanding and controlling those fundamental principles of fragmentation.
And you said this is just scratching the surface.
It is.
We could potentially do so much more with these drops.
We could.
It's amazing how scientific curiosity can lead us down these totally unexpected paths,
It is.
revealing possibilities we never could have imagined.
That's science for you.
But before we wrap up, I have one more question.
Yeah.
We've talked about controlling how the drops break, but what about the fragments themselves?
Oh, that's a great question.
Could we manipulate those too?
That's the next frontier, yeah.
So not only controlling how the glass breaks, but also the shape and properties of the fragments.
Exactly.
It'd be like creating a microscopic construction set.
Think about the potential for new materials.
Yeah, with completely unique properties.
We could design materials from the ground up, using those tiny glass fragments as building blocks.
It's like taking something that's known for its destruction and turning it into a tool for creation.
I like that.
It's beautiful, really.
It is, yeah.
So we've gone from the history of Prince Rupert's drops to the forefront of scientific research.
They have.
We've talked about microscopic fractures, engineering new materials, and everything in between.
It's been a long journey.
It has, but this is just the beginning.
There's always more to discover.
So keep that curiosity alive, keep exploring,
Keep asking questions.
and who knows what you might find. Until next time, happy diving.